and we can start designing anything, you know. So two-bit multiplier, right? Let's do it. Scheiße. Anyway, here is my box, right? A multiply B. You guys agree?
Yes.
A is 2-bit. B is 2-bit. Right? I don't know anything about circuit. If it's A 2-bit, what is the maximum number A can represent? Huh?
3.
3. B maximum number is what?
Also 3.
3. 3 times 3 is what?
9.
9, represented in how many bit?
4.
4. We are done. So the output P is represented in 4-bit. Right? And here is the multiplication sign. Right? Now, general rules, right? If A size, I was waiting for more. If A size M and B size N, P will be M plus N as a size. That makes sense?
Sorry, the 3 is the biggest number that the 2-bit could be, correct? Okay.
Okay, because you know it's 2-bit like this, 0, 0, 0, you know, 1, 0, like this, right? So this is the biggest ever I can get, right?
Correct.
Can you explain what the size M and size N mean? Like just any number?
Yeah. So you know here A is 2-bit, right? So in this case, A is 2-bit. M is equal to, right? B is 2-bit, so N is 2-bit as well, right? So P as a size, it will be 2 plus 2, so that's gonna be 4-bit.
Oh, that's it? Okay.
Yeah, that makes sense?
Yeah.
Okay, so let's build the design. Too stable, all right? So I have here like this. I have A and I have B. A1, A0, B1, B0, right? How many states this table is covering?
4?
Really?
16?
Oh, sorry, 16.
16, right? Why? Because 2, that means 4, 2 power 4, 16, right? So gonna be here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 12, 13, 14, 15, 16, right? 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. So far, so good. Output is in P, right? So P, it can be P3, P2, P1, P0, right? Here is M0, M1, M2, M3, M4, M5, M6, M7, M8, M9, M10, M11, M12, M13, M14, M15. Okay, now we multiply people, all right? So B times A is 0 times 0. Output is what?
0.
0. So till here, it's gonna be 0, right? Something 0 times something,
Yes.
right? So it's gonna be 1, 2, 3, 4, 1, 2, 3, 4, and 3, 4, right? The second, it will be 1 times something. So gonna be here 0, 1, 2, 3. The third will be 2 times something. So gonna be 2 times 0. 2 times 1 is 2. 2 times 2, 4. 2 times 3, 6. Then the fourth will be 3 times something. So gonna be 0. Then 3. Then 2 times 3 is gonna be 6. And then 3 times 3 is what? 3 times 3, 9.
9.
We finished. Right? Because how many K-map I'm gonna have? 4, right? 1 for P3, 1 for P2, 1 for P1, 1 for P0. Easy busy lemon squeezy or not? Does it make sense?
Yes.
So it was easy or not?
Yeah.
So it's just a time. It's a matter of practicing. That's the whole idea. Okay. Sounds good. Any question?
Can you draw out the circuit too?
You can draw the circuit. So what do you want to draw it with what? Multiplexer and decoders or demultiplexers, or you want to draw it with what? So 1 second. Hey, Prof, let me call you in like in half an hour, okay? Thank you. Thank you. Have a good one. Bye. Okay. So which way you want? K-map or? Okay, K-map. 1, 2, 3, 1, 2, 3, 3, 4. Yeah. Right? This is left to right, right? So A1, A0, B1, B0, 0, 0, 0, 1, 1, 1, 1, 0, right? 0, 0, 1, 1, 1, 0, right? Location 0, location 1, location 3, location 2, location 4, location 5, location 7, location 6, and location 8, location 9, location 11, location 10, location 12, location 13, location 15, location 14, right? I mean, P3 is straightforward, right? Everybody can see, right? Everything's 0 except the situation, right? So I'm not gonna make P3 because P3 is like 1M term. So it's basically gonna be A0, A1, B1, B0, right? So it's gonna be A1, A0, B1, B0. This is actually B3. It doesn't need even K-map, right? Everybody agrees with me? Hello?
Yes.
Yes.
Okay. Let's go maybe to the P2. So, let's make this for P2, right? So P2 as a function of the A1 and A0 and B1 and B0 is equivalent to M10 and M11, right? M10 and M11, and then M14, right? And M14, and the rest are zeros. Right? You guys agree?
Mm-hmm.
So in that case, how many things are gonna be? It's gonna be group 1, group 2, right? So it's gonna be here group 1 and group 2, which is equivalent to group 1 is what? So gonna be A1, right?
Mm-hmm. Complement.
And then we're gonna go like this, right? So they're gonna be what? They're gonna be B1. Or then this guy, right? That was this guy basically. No. Sorry. I think
No,
I
that
made
was
something.
that was the vertical one, I think.
That was this one, I believe. That was this one. Yes. That was this. let's go for this, right? No, I made a mistake. If you're
Yeah,
gonna go
it
just
should
with this,
be-
it's gonna be A1, A0 complement.
Yes. That's correct.
Then this one is gonna be A1 with those two, right? Which is gonna be B1, B0 complement. Okay, so we have P3 in our hand. We have P2 in our hand, right? You can make P1 and P0, right?
Yep.
So it's straightforward. Then you can implement it with multiplexer, decoders, whatever, right? The other methodology is actually to say A1, A0 time B1, B0, B1. Then you just go like this. It's gonna be A0 time B0, A1 time B0. Then you will go ahead and just do it like this. It's gonna be A0 time B1, A1 time B1, and then you start adding. So this will go like this. It's gonna be A0 time B0, and that will be P0. The second will be adding this to this, right? So gonna be bringing to me P1. Then you know there will be a carry out of this adding, right? So gonna go here. So that we called C1. Then you know C1 will be added to this to bring P2, and the carry out of A1, B1 with C1 will bring C3 or C2. C2. So then you know C2 will be P3. So you already have those two. This is the second one. So does it make any sense? Any question? Any problem so far? Hello?
No.
Hmm?
I have no question.
Okay. What about the rest of you? If there is no question, we can move forward to some other problems. Like for instance, you know, what about if I would like to build a circuit performing adding and subtracting? What should I do?
Sorry, say that again.
I would
If you
like to
wanted
build a circuit,
Mhm.
implement a circuit, which will add and subtract at the same time.
So you would need another.
Hmm.
You would need like a button that switches between adding and subtracting, right?
Maybe. Everything is possible in this life, right?
Would
So
you use
basically,
a full
F-
ladder?
Yeah, F is A plus B, and this is adding, right?
Oh, two complements.
Two complement.
Yeah.
So F is A subtracted from B, which is subtracting, right? This
Yeah.
one is basically A, B complement plus one.
Yeah.
This is 2's complement,
Mhm.
right? So in that case, you need to use a full adder. Why full adder? I will show you. Imagine that, you know, I'm building a circuit performing 4-bit adder subtractor. So I'm designing 4-bit adder subtractor. So what should I do? I have done it in front of you before the full adder, right? So the full adder is like this, right? FA. It has 2 inputs, which is A and B, and it has carry in, and it's have carry out, and it has the sum. Correct?
Yes.
And if you remember the equation, it's basically A XOR B XOR C input, and the carry out, it was A with B ANDed, A with C in ANDed, B with C in ANDed, right?
Yes.
We have done this many times. So in this case, if I have A0 going with B0, it's gonna bring me S0, right? And I have here a carry in, and the carry out, I will call it C1. Then full adder. And then I will go like this, another full adder. If I have here A1 with B1, it's gonna bring me S1. And then that will bring me a C2. Then I can go into another full adder. Then it will be B2, oh, sorry, A2, B2, right? And it's gonna bring me S2, and I'm gonna have C3. And then if I take C3 one more time like this, it's gonna be A3 with B3. They're gonna bring me S3, and there is a carry out officially for this. So what I have in front of you now, it's a 4-bit full adder, right?
Yes.
That makes sense to everybody, or it doesn't make any sense? You know why I'm doing this C1 passing to the other one, right? Look at this, right? 1 0 1 1 0 added to 0 0 1 0 0. What are you doing? Tell me. You're adding 1 to 0 and you're getting the output with the carry of it. 1 plus 0 doesn't have any carry, so the carry out here 0. Then 0 plus 0 plus 0 gonna be 0, and there is a no carry out. Then you will move 0 plus 1 1 1. It's gonna be what? 0, and there is 1 here. And then that 1 will go here with 0 and 1. It's gonna be 0 and still 1. And there is 1 will go here and gonna be like that. Let's match it on the circuit, right? So 1 and 0 added, it has 1 here, and the 0 will go here. That 0 will go with the A1, in this case 1, B1 in this case is 1. They will work together to bring S here, and then the carry out, which is the C2, will go here, and then you will move forward. So that does make sense?
Yes.
Yeah.
Okay, so now we have a circuit actually is adding, right? Everybody agree with me, right?
Yes.
It's not completely adding. You know why? Because if you notice here, this is not, the first stage is not full adder. The first stage is half adder, right?
Oh, that's why you have the carry in. So you have
Exactly. So the carry in has to be what? 0,
0.
which is the upper half of the upper half of full adder is a half adder, right? That makes sense?
So can you say that the
Again.
adder?
I want everything in this life is like a piece of cake, CIAB, right? Right?
Yep.
This guy, it's a third. So 2 power what? 2.
2.
So that means would be 4 zeros and 4 ones. So the upper half 0 is is half adder.
Oh yeah.
Oh.
$5. Okay, sounds good.
That's good.
That makes sense. Anyway, now this lovely circuit need a slightly change, and it will turn to be an adder and subtractor. It's just it's like Lego. How are we gonna do it?
You need a controller.
Yeah, we're gonna see what is this control. Let's play it step by step until we will drill it into a very nice gate. Okay. So imagine the following. First of all, this circuit, to perform subtraction between A and B, it has to have 1 here, right? Because it's gonna be A plus B complement plus 1. Who will give me the 1? That's CI. I will turn it from 1 to the 0, then it will look into the second part of the table, right? Okay, that's first thing. Second, this B0, it has to be what? B complement. You guys agree?
Mm-hmm.
So that means I can draw this circuit like this. Full adder, CI, C1, full adder, S0, S1, C2, full adder, S3, C3, full adder,
C2.
C2. Yeah, come on, I can just call it whatever. I can call it Muhammad. It doesn't matter.
Yep.
Just name. Anyway, so we have here what? A0, and we have something here. We have here A1, and we have something here, and we have here A2, and we have something here, and we have here A3, and we have something here. Right? That's something, it depends on the CI. How? We learn from our study, there's some things called multiplex. You guys agree? So I can pretty much do it like this. A multiplexer having in 0 location B 0, in the A location, the negation of the B. And there is selector. Let's call it selector, right? Then the same thing. So I have here a multiplexer 0 and 1. They're gonna be B1, right? Then I can have here a selector. Then I can make another multiplexer like this, 0, 1, and I do like this, and I'm gonna be B2, and here's selector. And then I have here a selector for multiplexer, and it go like this, B3, and here is selector. Do you guys agree?
Yes.
So look at this, it's really fun. Why? Because CI, when it's 0, I have to be sure all the selectors will be 0, right? Everybody agree with me?
Yes.
So when CI is 1, I need to be sure select will turn to be 1. So what should I do? Just put a
Flip them
wire.
all together.
Exactly. So I have to put a wire. Here is the wire. So what I have in front of you is an optimized version of the 4-bit and optimized adder subtractor. Somebody will tell me why you're saying it's unoptimized. I will tell you why. If you look very carefully to the circuit, there is a way to optimize it. Would you imagine that? So let's see what Professor is talking about, right?
Well, the multiplexer has like an AND gate and stuff like that inside it, right?
Now I will show you now. Anyway,
Yeah.
so if I take this and I have like a telescope or whatever, to take it by itself, expose it out. So it's gonna be like this, right? Right? Everybody agree with me?
Yeah.
Yeah. So look at this circuit. This multiplexer, if you guys remember, it was an AND, and it was an AND, and here is our lovely OR, and it has B, and it has Scheiße. Like this, right? Are we done? Nope. We have to have a selector, right? So here is our selector, and this selector will be like this, and it go like that, right? How many gates we have here?
5 gates.
5.
A lot for me.
A lot.
Yes. Critical pass is basically very long also because, this is the longest pass I can have. Right? All right. I mean, same thing, Those are the 2 longest, right? If we remember from our discussion, we can figure it out from this table, making a table with B and P and all of these things, or we can think about something else. Everybody know what is XOR, right?
Yes.
So there is a table of XOR saying that if A is XORed with B, so there is how many states this table will be covering?
4 states.
4.
4 states. And 0, 1, 1, 0, right? Okay. So if one of the inputs of this table will be considered select, if one of this input of this table will consider what select, what will happen? So if I consider this guy my select, right? look what will happen. So when is equal 0, this is the output, right? The output will be B. You guys agree?
Mm-hmm.
But if the select is 1, what will happen? So this output will be what? B complement.
B complement, yeah.
So I can literally say that, the circuit I drew up, it's basically what? B with select. So this guy equivalent to this guy. Any question? Any question? Any answer?
Can you explain why you did the multiplexer again for the subtractor, right? To get the B complement?
Yeah. I mean, think about it. I have two choices, right? If I looked at this equation, right? Look, A plus B or A plus B complement plus 1, right? But every single input here, right? It has A and B. That's it, right? So that means, the second one, it has to be what? Selected, right? I select B or I select B complement. Do you agree?
Correct.
You understand what I'm saying?
Yes, thank you.
Yes. Okay. Now it makes sense. So this circuit, it can be redrawn, right? In a way that I can draw it like this.
Sorry, Professor, if you go back, so it'll be A plus B plus 0, right? Will that be it?
Yeah, exactly.
Yeah. There we go.
Right.
Yeah.
Then this guy is the CI, right?
Yep.
Yes. Okay. So anyway, drawing it, it's gonna be here S0, CI, A0. Right? B0. Now it makes sense? Huh?
Yes.
Okay. So we figure out how to build 4 bits as a subtractor, right? And what I actually described to you today, it's called, to be very, very specific, RCA circuit, which stands for rebel carry adder. What does it mean, rebel carry adder? It means that, this input, this output is belong to the, and depending on this output. And then, so if you have n-bit adder subtractor like this, so the adder units doing the bit number n will be waiting for every single bit to be finishing the process before this guy will be working. Do you guys agree? Which is end up being T delay of the full adder n bit is equivalent to n times the delay of 1 bit full adder. What does it mean? It means the following. This one has to wait for this one to finish. Do you agree? So that means that C1 is the one is actually causing me to what? Delay, right? Because C1 is going into the equation of the S1, right? Because, think about it, right? You can write it like this. C1 is equivalent to A1 plus B1 plus C1. Here's C2, I'm sorry. So the C1 with A1 and B1 will be added together, and that will bring me the C2. Right? And you move forward. Does it make any sense to everybody?
So what is the T delay? So is it
The
just
delay,
like,
the delay. How much
okay.
time this will take?
Okay, so yeah, so you have to do the first one before you go to the next one.
Exactly. So you know how many repeated blocks will have times the delay of one of them will give me how much time the whole entire circuit will take to give me an output.
Oh, gotcha.
That makes sense to everybody? Any question? Any answer? Anything?
Yeah, so the N is the block and the T delay is
Number of blocks, yes.
yeah, and the T delay is
Exactly.
Is T delay given to us, or do we need to how do we calculate T delay?
Oh, come on, you calculated before. You forgot?
Oh, it's the critical path.
Yes.
Got it. Thank you.
Yeah, welcome. So you know, T delay of anything is basically the longest path or the critical path.
So after for the subtractor, right? We're just gonna get the complement. So then we have to do the ones complement again, right? Or the twos complement.
Where? No, you don't need anything. This is just a circuit
the-
performance for you. I mean, now we are talking about
subtractor.
different story. You're talking about, you know, it's signed and unsigned. This is actually unsigned work. The whole entire circuit I built for you is unsigned now, right? There is no sign here. You understand what I'm saying?
Mm-hmm.
Sorry, Koos, can you repeat your question again?
I was saying that for the subtractor, right? You're not gonna get the genuine answer. You have to do the complement of it, right? So
Yeah,
Would you have
this is something else. It's what you're talking about now is completely different story. What you're talking about now, you know, which one is bigger and the other one will be bigger or not, so the output will be negative. Then you know I have to just complement it one more time. Then it will be the number negative something, right? This is the
Yes.
representation, not the brain of the computation.
So that's like upper level, higher level.
Yes, you keep
Yeah,
adding
yeah,
if
yeah.
you want. Yes, because you know you have to build a cascaded circuit, right? Like one pass to one pass to one, then you know the whole circuit will be a system.
Would you still do it with a full adder, or is there another?
I mean, you're gonna do something as a full adder, right? So by the way, don't mix. There is something is called signed adder, and there's something is called unsigned adder, right? Because in a
Okay.
signed adder, you have to use comparators as well, because you have to compare between values to see who is actually in greater and who is lower, so the negative or positive will come out. That makes sense?
That's a thing. Okay, interesting.
Okay. Anyway, so the rebel carry adder, it's a circuit approach. It's a naive design. It's a very simple design, but you know it's limited design. So you know, rebel carry adder is used for the low power application, like IoT, Internet of Things, iWatch, smart sensors. There is another design called CLA, which stands for carry look ahead adder. This one, it costs you more gates, but it will be more optimized in terms of performance. So the delay will be significantly going down. But you know, this one, I'm not gonna talk about it now. When we finish the whole entire course material and I still have some time, I can actually go through it. Okay? Because it needs a lot of tricks.
Are we halfway there, or
We are
how
almost.
much more?
I mean, we are, no, we are actually halfway. Because you know, we're gonna go in the sequential, right?
Mm-hmm.
And then after the sequential, you know, we have time, I will go into processing and stuff like that. Okay, Luke?
Yep.
Is there any question regarding this part? Is it straightforward? Is it easy peasy lemon squeezy?
Yes.
Okay, so now we're gonna go into the comparators. Have you guys heard about comparators? So if somebody telling you design 2-bit comparator, what are we gonna do? So let's think about it, right? here is a box, it's called Comparator, right? It has two inputs. It has A and it has B, right? This is 2-bit and this is 2-bit. What type of outputs I should get from the comparators?
Another 2-bit?
Are you sure? Why 2-bit?
Because you're comparing A and B, right?
Okay, so what
So, yeah.
what expecting out of this comparison?
Either A or B.
Or A is equal B?
Yeah, so it would still be 2-bit.
It would be 3-bit.
What?
Yes, you know why? A greater than B, right? A less than B, A equal B. Right?
Oh, you're not just gonna get an output. You're just okay. It's gonna actually
Yes.
okay.
So that makes sense.
I thought it was just gonna spit out either if it was A or B or something like that.
That would be, then you have to spend more cascaded one. Anyway, so this is more general. Somebody else will tell me, what about B and versus A? Who cares? Because end of the day, you can flip the input, right?
So are you gonna get something like 1 0 0 and the one at the very top will be the correct statement?
No, basically, I'm gonna follow the same footsteps of this, right? This, right? If I go like this, I will just go ahead and say that, my truth table, it's gonna be also how many bits will be covering. It will be A covered with B, right? A1, A0, B1, B0. Then, I have here what? 1, 2, 3, right? Low equal high or greater, right? Less equal greater, right? Then, how many states this table will be covering?
16.
I want to say 16.
Okay, so when you say I want to say, are you sure about it, 16 or not?
Yes, because A1 will cover from 8 to 8.
Because A and B, every single one is 2 bits, so that means total inputs are 4 bits, so that means 2 power 4 is 16. That's it. So it's gonna be here like 1, 2, 3, 4, 5, 5, 6, 7, 8, 9, 10, 11, 12, 13.
Wouldn't you essentially say it just depends on A1?
Yeah, but what I want to say that my general rules from day one, if you remember, we'll talk to them later. Anyway, it's going to be 2 power number of inputs, right? Number of inputs in terms of bits. So 1, 2, 3, 4. It's going to be 2 power 4. Okay, that's basically my rule. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Then here gonna be 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and then here we're gonna be what? 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Right? And M0, M1, M whatever, right? So A and B are 0. So this is equal or greater or less or what?
It's equal.
Equal. And you will move forward. You fill the table and you can make K-maps, or you can make it with multiplexer, you can make it with demultiplexer, you can make it with decoder, you can make whatever you want. Do you agree?
Yes.
So should I continue it or I shouldn't?
Nah, you're fine.
It's perfectly fine for everybody, right? I will say here homework. Do it.
So are we looking at A is greater than B and so A would be the first one? Because then the second one would be like B is greater than 1, so it would be, B will be greater than A. So-
here, L is, A less than B, right?
Okay, got it. Thank you.
Greater is A greater than B, right?
Is there essentially, is it like the first input will be the one that you're comparing it to, or does it?
It's up to
It
you.
matters, right?
It doesn't matter. But you have to, when you say it doesn't matter, that means you have assumption, you stick with the assumption. Right?
So okay.
I mean, if you put A here and you put B there, right? I don't care, but I'm just following the rule, right? That makes sense?
So if you put B on the other side, would it be B is less than A? Is that what it would say?
No. It's up to you.
Oh.
What I'm
okay.
saying, you define your own rules, but you stick with
Gotcha.
your rule for the rest.
Gotcha. Okay.
That makes sense?
Do you think we can go through the table just like
Yeah.
for clarification that we're not lost? Because I'm getting kind of lost on the table. Like, okay,
Are
which
you
one's
lost in
less, which
this?
one's
Come on,
equal?
look, 0, 0 and 1. Who is greater? 1,
A is
right?
greater.
One,
So
yeah,
A
who's
that
greater?
means less than B. Do you agree?
Yeah.
A
So,
less
yeah.
than B.
So L, yeah.
0 and 2, A is less than B. 0 and 3, A is less than B, right? Now, 1 and 0, A is greater than B. Then, 1 and 1, they are equivalent. Then, 1 and 2, so that means is less, right? And then, 1 and 3 is less. Then, 2 and 0, greater, right? 2 and 1, greater. Then, 2 and 2, equivalent. Then, 2 and 3, less. Then, 3 and 0, greater. Then, 3 and 1, greater. Then, 3 and 1 and 2, greater. Then, 3, 3, equivalent. That makes sense? Huh?
Can you scroll down a little?
Sure.
Easy
So for
peasy.
the middle one, would I have like 4 OR gates? I always get confused. Do you do AND or how do you tell?
What end?
So you have 4 ones, right, in the middle.
Okay, you mean this and this? This
No,
is
no, no,
3 and
in-
this is 3. Okay.
In the middle, like the outputs, there's the 1, and the 1 on the 15, the other one, and then the very top one.
You mean this? Or this? What?
He's talking about E, the E.
E.
That's
So
C,
there's like-
D, E here. Okay. What? This is E, right? And this is F. So
No. No, I mean E, like equal. The outputs for E, the ones.
Yeah.
Yeah, the ones. So are those ORed or are they ANDed? I forget.
There is no and or here. It's just A and B. A is what is the value and B is what is the value. Are they equal or not? E is equal. Right?
If I were to make this into a logic gate implementation, would I not
Logic gate
use?
implementation, I'm gonna use the K-map, right? Because
Okay.
look, here is 1, 1, 1, 1, 1, right? Do you agree? So we have to go and put it in the K-map, right?
Yeah, let's do the key.
Wait. We will make the K-map
Wait.
for it. 1 second.
Yeah, that's
Right? 0, 1, 3, 2, 4, 5, 7, 6, 8, 9, 11, 10, 12, 13, 15, 14, right? Let's go for E. E is basically M0, right? Then M5, right? Then M10. What's 10? Then M15, right? You see that? So what is this? they're going to be 4 terms, right? So you can come
Yeah.
and say E is equivalent. This is a group, this is a group, this is a group, but this is a group. They cannot intersect, right? So basically, no, they're going to be A complement 1, A 0 complement, B complement, B 0 complement, or with what? A1 complement A0 with B1 complement B0. Then here gonna be A1 A0 with B1 B0. Then the last one is gonna be A1 with A0 complement with B1 B complement, right? Do you agree?
Yes.
Okay, so what was the question?
Sorry, I got my logic mixed up with the decoders. That's why.
Okay.
I get it now.
Okay, super. Any question? So it's supposed to be easy peasy lemon squeezy, right? So we can build it with anything we want. We can build it with decoder. We can build it with, you know, anything, right? Sounds good?
Yeah.
Any question? Any concern? Any answer? Anything? Okay, so we can summarize what we learned today, right? We talked about, you know, the multiplier as an exam question. And we found it, it's easy peasy lemon squeezy. Then we talked about adder, subtractors, and we discussed about how can we do it using the two's complement. And we studied how can we make optimization from thinking of multiplexer going into XOR. Then we moved the gear into what? Comparators. All of those guys are under the umbrella of what? Combinational what? Circuit. Any question?
Are we moving into sequential then?
No, still, you know, there is more combination. There is one more lecture, maybe, or 2 more lectures for sequential, for the combination. You know, the most important thing for me to see that you guys understand what I'm saying. Then I can move forward to the next step. That makes sense?
Yes.
Because if I keep adding more difficult levels, that will make it more hard for you to understand what's going on, right?
What's the difference with combinational and sequential?
Huge difference.
What? Oh, okay.
Sequential, you know, combinational, everything gates. Sequential, there is element act as a gates, yes, but is actually running with time. And running on something is called clock. And we're gonna describe what is the clock and all these things. Like for instance, the clock is basically a train of pulses, right? It has a periodic thing, it's called T. So this thing is repeated and the distance between this and this are equivalent. Many stories and using RC, you know, do you remember the RC charge? You know, I'm charging, this is charging, I'm charging, this is, do you remember this?
Oh, the waveform?
The time constant. You remember tau? Tau R times C, which is the time constant. Yes.
Mm-hmm.
And then, you know, if you flip the time, you're gonna define something is called frequency. It's a fun story. It's even easy peasy lemon squeezy than combination. But I don't want mixed stuff. Okay.
Yep. Sounds good.
Super. So if there is no questions, I would like to thank you for the time and for attending the course and even attending the lecture today. And I'm looking forward to talk to you on Wednesday. I have many deadlines, you know, with NASA, Illinois, some other places. So, you know, I will be still working on the weekend, maybe for grading you guys. Everything will be posted on the Blackboard because still I have to put this grading system in the Blackboard. Then, you know, if anybody have any confusion about some questions or grade or whatever, you know, you are more welcome that, you know, we can go through it together. Okay.
Professor, can you share, put a link on the Blackboard towards grade scope? Because right now you just need to go like in the web, the email, and then you click on it, and you can click on it.
But you know, grade scope, see, you mentioned, you know how to click it, right?
I just gotta open the email each time I want to check. That's all.
Yeah, come on.
Okay.
come on.
I'll make it less work.
And
It's okay.
wait. I will tell you something. Wait, just wait. You know,
Yeah.
when I will release the grade,
Uh-huh.
you do not see just the grade in the Blackboard. You will also get a link saying that, you know, Professor Ali released the grade. You click there in the grade scope, then you will see every single question and even the parts of the grades.
Okay.
So, you know, it's really fun, you know, don't worry. But don't
Alright.
forget, the one who's grading you is AI, is not me.
It's AI.
Yes.
I don't trust it.
No, I trust it.
I don't trust it.
I'm the
I
one.
don't know.
I'm the one who built it, so I trust it. So.
Oh, okay, you built it. Okay. I was gonna say it's like, you know, it's like the autonomous vehicles. It's like I don't know about that yet.
Oh, wait. You know, the autonomous vehicle now, if you just jump in front of autonomous vehicle in the middle of the street, it will stop before it will hit you.
Wow.
It does like so many checks.
Oh,
There's so many
I just saw a video that, you know, there was a car that was like blocked. So it was following another car, and then the front car swerved off, and because there was a car in front of it. It didn't have enough time to stop and hit it. So
anyway, yeah, don't worry. But you know, here, you know, I don't know if you can see my camera or not. You know, I'm building stuff now for the autonomous. You know, can you see my camera? No, they cannot see my camera.
I'm just checking. Yeah, I'm looking
I'll
at it
show
right
you.
now.
You have a background.
I know.
You're in space, sir.
I use it, you know, for a specific reason. Here, look.
You're building a
Is that
drone?
you building?
Yes, I'm building now. You know, I'm gonna build like a swarm of the drones. It's like around 25 drones flying together.
Oh,
And they will be charging each other.
They're charging?
Wait, charging? Like
How do you charge in the air?
They're gonna be docking.
What?
Yes. So you know,
Wait.
it will be the first docking mechanism ever for drones.
what? That's so
Yes.
cool.
Yes. Are you guys following the RESCA? The RESCA competitions?
Resta?
RESCA. I should send it to you. So I have here my teams representing the university for on campus for the CSU system. I will send you the work. So everything is actually based on this digital logic. So you know, do your best. You know.
I want to play with that.
Yeah, so you know, you have to, you know, you have to love 2300. You know, somehow.
No, I want to learn that. I don't want to play with that.
Okay, get the link. Check the link.
Sounds good.
Okay, you will find that, you know, the nominated for the College of Engineering and Computer Science is my teams. They are working in a post-quantum computing. Okay, so there's a ton of ideas you can do with using digital logic design. That's why I want you guys to work hard on the digital logic design. You can do a lot of amazing stuff, and you can be even, you know, when you graduate, a digital engineer, digital designer, or digital design engineer. Any questions? Any concern? Any answer? Anything?
Nope, it was good. Thank you, Professor.
Super.
Yeah,
So
thank you so much.
God bless all of you, and it was my pleasure to talk to all of you. And you know, hopefully everybody will have a nice and safe rest of the day. Okay. See you on Wednesday, and once I finish, I will load everything to the Blackboard.
All right. Have a good day, Professor.
Thank you. God bless. Bye.
Bye.